Okay, so let's get started here. It says find the derivative with respect to x of x cubed. Notice your variables here match. When your variables here match, you're differentiating just like we've always differentiated. So the derivative of x cubed is 3x squared. Drop the power. It's just the power rule, okay? Now what I want you to notice in the next one, you have the derivative with respect to x of y cubed. The variables do not match. Anytime the variables do not match, you have to use the chain rule. So the derivative of y cubed would be 3y squared, just like it was with 3x squared, except because the variables didn't match, you need to put the y prime. Again, in the book, they would have put dy dx in this case. Okay? Let's look at the next one. What's the derivative with respect to x of x plus 3y? Well, the derivative of, you got to be careful which ones match and which ones don't match. The derivative of x with respect to x is just a 1, plus the derivative of 3y would be 3 times 1, you would think, but that's not what it is. It's 3 times y prime, because remember, the derivative of y is y prime. How about the derivative with respect to x of xy squared? Well, hopefully you see that this is a product rule where you have a first function and a second function. So what's the product rule? It's the first, which would be x, times the derivative of the second. Well, the derivative of y squared would be 2y y prime, plus the second, which would be y squared, times the derivative of the first. Well, the derivative of x is just 1. Of course, you could simplify this at that point in time. Okay? So, what is implicit differentiation? What are you going to do? You have an equation that's in implicit form. In other words, you're going to have variables on both variables all over the place. Maybe on the left side, maybe on the right side, maybe on both sides, okay? But it's an implicit formula. You aren't going to be able to solve for y, like as in example 2. So what you're going to do is instead you're going to take the derivative with respect to x of both sides of the equation, and then you're going to solve for y prime. So take the derivatives like we just did and then solve for y prime. So let's go ahead and do that with example 2. The first thing we want to do is take the derivative with respect to x of both sides of this equation. If the two sides are equal, then their derivatives are equal, okay? So let's differentiate each term individually. What's the derivative of y cubed? Well, that would be 3y squared. Don't forget your y prime. Plus, what's the derivative of y squared? Well, that would be 2y to the first, or 2y times, don't forget that y prime. Minus 5 times the derivative of y, again, that's y prime. And then minus the derivative of x squared, it would be minus 2x. And then on the right-hand side, we'd have the derivative of negative 4. Derivative of a constant is 0. So what do we want to do? We want to isolate y prime. So everything with a y prime stays on the left. Everything else goes on the right. So I'm going to add 2x to each side. That's going to leave me with 3y squared y prime plus 2y y prime minus 5y prime equals 2x. Why did I do that? Because now every single one of these things should have a y prime on the left-hand side. So factor it out. So if we factor it out, on the left-hand side, 3y squared y prime, take away that y prime or divide by y prime, you'd be left with 3y squared. 2y y prime divided by y prime would just be 2y. And minus 5y prime, take away that y prime, you would have a 5 left. So I have y prime times the quantity 3y squared plus 2y minus 5. Now we need to solve for y prime, so we're going to divide both sides by 3y squared plus 2y minus 5, both sides. 3y squared plus 2y minus 5. And that's going to give us our final answer here of y prime equals, sorry, let me use black. Y prime equals, on top we have a 2x, on bottom we have 3y squared plus 2y minus 5. That is implicit differentiation, okay? So, what did we do? Take the derivative of both sides, isolate y prime, get everything with the y prime on one side, everything else on the other, factor out the y prime, solve for y prime. Notice the difference though. Because our equation had both x's and y's, oftentimes it'll happen that your answer has both x's and y's. And that's perfectly fine We solved for y prime, which is dy dx, exactly as they asked. Let's go ahead and try a little more difficult example. Example 3. It says find dy dx for the equation xy squared plus 4xy equals 10. Again, here's an equation that we could not solve for y. So this is an implicit function. So we need to figure this out. We're going to take the derivative with respect to x of both sides of this equation. The derivative with respect to x of both sides of this equation. Okay, let's look at this first part right here. What's the derivative of xy squared? I'm going to underline it with color so you can kind of see where I'm going here. Well, that's going to be a product rule because it's x times y squared. So the product rule is going to say it's the first, which is x, times the derivative of the second. Well, the derivative of y squared would be 2y, y prime, plus the second, which is y squared, times the derivative of the first. Well, the derivative of x is just 1. So that right there is just the red part, plus, now we need to find the derivative of the blue part, 4xy. Again, this is a product rule. It's 4x times y. So we have to do the first, which is 4x, times the derivative of the second. Well, the derivative of y is y prime, plus the second, which is y, times the derivative of the first. The derivative of 4x is simply 4. So there we are. There's the blue part. Equals, well, the derivative of 10 is quite simply 0. So I'm going to clean this up a little bit. It looks like I have 2xy y prime plus y squared plus 4x y prime plus 4y equals 0. Again, anything with a y prime stays on the left. Anything else moves to the right. So I'm going to subtract y squared from both sides. And I'm also going to subtract a 4y from both sides. So when I do that, on the left, I'm left with 2xy y prime plus 4x y prime. On the right, it looks like I have a negative y squared minus 4y. Why did I do that? Because now everything on the left has a y prime, meaning I can factor out a y prime. So let's do that now. If I factor out a y prime, what would I have? Well, 2xy y prime divided by y prime. What's left is the 2xy. 4xy prime divided by y prime, what's left is the 4x. So when it factors into y prime times the quantity, 2xy plus 4x. Now let's divide both sides of the equation by that 2xy plus 4x. And I end up with y prime equals negative y squared minus 4y all over 2xy plus 4x. Is there anything I can do? Anything else I can do? Well, there is probably, maybe something I can do. For instance, I see a negative sign on top and I see a y on top, so I could certainly factor out a negative y there. I see a 2x that I could factor out of the bottom, so I could try factoring that there and see if there's anything else that really happens there. But in all honesty, it's not going to do me any good. Personally, I'm just saying, look, that's the final answer. Okay? If you want to go further, you could have said, let's factor out the negative y, then it would have given me a y plus 4 on top. And on bottom, you could have factored out a 2x, which would have given me a y plus 2. See, it doesn't simplify at all. So there was no need to do that. Okay? It was totally worthless to do that. But that's up to you. If it did simplify, we would have wanted to simplify.